Hello, this is my first video here in YouTube. Welcome to my channel. We're gonna talk about tensors. No, not this lamp from Staples. So Google announced a chip that will be inside their upcoming Pixel 6. They got sick of those rumors spreading about the Whitechapel chip, so they invited some YouTubers to see a prototype of the Pixel 6 and told them a few things about it. The chip has an official name, Tensor. It was named after Google's AI chips called TPU or Tensor Processing Units. One of those videos is by Gary Sims. He did not get to see the Pixel prototype, but he talked about the chip. Gary said that naming it Tensor is a bad idea because so many things are named with it. And I agree with him. One thing he mentioned was the dictionary definition of tensor, a mathematical object analogous to but more general than a vector, represented by an array of components that are functions of the coordinates of a space. When I saw this, I was like, that looks familiar. I guess tensor is an original math word, and it is what I thought it was. Today I'm gonna show you what tensor is from the point of view of differential geometry. There is an algebra version of tensors, and by algebra I mean abstract algebra. It is more general, but I will not talk about that. We're gonna go over the differential geometry tensor. When I thought of making this video, I searched for videos about tensor to see if someone made a video about it. There were plenty. Some are about physics, some are about machine learning, some are about TensorFlow, the language. Many of them say that a tensor is a generalization of a matrix, which they say is a generalization of vectors. They all look vectors to me. Here are my main references. A book by Mike Spivak and a book by Jack Lee. A tensor looks like a matrix. A matrix can be one column or one row. No, not that. Here, a row matrix. Sometimes these are called column vector or a row vector. What can we do with matrices? We can add or subtract two matrices of the same size. We can scale them. We can multiply two of them provided that the sizes are compatible. A tensor can look like these. They have rows and columns of numbers, but they can also have layers of numbers. So this is a 2 by 3 by 4 tensor now. 2 by 3 by 1, 2, 3, 4 tensor. Like 4 layers. And they can even have more bys, like 2 by 2 by 2 by 2 tensor. Okay, 2 by 2 by 2 by 2 tensor. Just like matrices, we can add two tensors of the same size. We can scale tensors, but we don't really multiply them like we do with matrices. More on that later. What do we do with them? We plug vectors into them. The output is a number, like one number or a 1 by 1 matrix. For example, this is a 2 by 3 tensor. We plug a pair of two-dimensional vector and a three-dimensional vector. The output should be one number. We plug vectors like these. This go to here. This go to here. The tensor goes to the middle, and we multiply them like your ordinary matrix. The output is one number. Now, what if we have a tensor with layers, like a 2 by 3 by 3? Like this. Okay, so since this is a 2 by 3 by 3 tensor, we plug a 2D vector, a 3D vector, and another 3D vector in that order. The output is one number. I just made up the word layers. Nobody really calls it like that. So how do we deal with this? So we take this first column and we put labels in them. So this first layer here, we put labels. We take the first column and we put 1, 2 here, like that. We do that the same for the next columns. 1, 2, 1, 2. Now, the first row, we put 1 on all of them. No, we put 1, 2, 3. Okay, and the second, we put 1, 2, 3 as well. 1, 2, 3. Just as we would label a matrix. Now, since this is the first layer, we all put 1 in them. 1, 1, 1, 1, 1, 1. Okay, now do the same with the second layer. 1, 2, 1, 2, 1, 2. 1, 2, 3. 1, 2, 3. All of these are second layer. So we put 2 on all of them. Like that. And then do the same thing with the third layer. Now, if you notice, the labels that we have 3 numbers in them. So A, some number, some number, some number. We don't really use the square boxes, but what we use are letters, IJK, or we call them indices. Now, how do we turn all these into one number given the vectors? Here's how we do it. We take 1, 2, 3 here, for example. A123 is -4. Let's go to the next page. So A123 is -4. Multiply that by the first entry of the first vector. So that's 3. So the next is 2 here. We take the second entry of the second vector, which is 2. Next, we take the third entry of the third vector, which is -2. We multiply them all out, and the result is 48. Okay, so there are 18 total multiplications here, and we did already one. Just do that 17 more times. The result is all these. So we do all these multiplications and then add them all up. The result is -210. That's it for this video. Thank you. I hope to see you again sometime later. Bye.